Thank you for staying for this talk. I want to thank the organizers for their efforts to keep going this conference in the middle of this pandemic situation. So this talk is about the superconductor superfluid density from the crossover theory that includes two whole copper pairs. This is a theoretical work here in the University of Mexico, in Mexico City. This is part of our theoretical book. So this is the outline of this talk. We have some motivation to do this work. I want to mention some background about the holes in superconductivity. Briefly, I want to describe the GBC theory, a generalization of the Gaussian condensation for image the BC as Gaussian crossover. So the results, the superconductor superfluid density, and lastly some conclusions. So our motivation is that BCS theory results are limited to describe superconductivity below 4 Kelvin. Another motivation that we have is that BCS is related indeed with BC. This, the answer can be in some problems with some of you, but my answer, well, our answer is yes. Another motivation that we have is this question. This question we have made for a long time ago. Is superconductivity with holes relevant at all? And the answer for us at least is yes. We have 5 critical points on the important role of 2HCPs. Later, I will describe the 2HCPs, and I let you these 5 critical points. I hope that some other time we have time to describe these 5 critical points. So this is the background. Holes in superconductivity, maybe the first time was mentioned by Frankel in 1937. After that, Newton Bernardes in 1957 talk about the holes. The problem of electron-hole couplers was examined for the first time in the work of Keldysh and Kopaye, and more recently in the 80s, at the end of the 80s, Jorge Hirsch in the University of California at La Jolla in San Diego made a whole theory of superconductivity. This is a good, interesting review about the electron-hole superconductivity. So the superfluid density, many of you is probably that know that this history in 1938, Kapitsa published his paper about the superfluid density, and also Allen and Missener. The peculiarity of this both paper is that published in the same volume, one after another. So the Kapitsa claimed that this phenomena is analogous to that of superconductor. We will follow this picture of Kapitsa in this work. So Landau, after that, introduced the concept of the fluids, but with no connection to the BC. So the existence of superfluids turns out to be linked with BC. This paper of Baliban is very interesting. I recommend to you, because at least he says that indeed is related with those statistics. And the Leggett, his famous paper in the early 1970s, note that helium atoms could in fact form BCS-like pairs. So let me give to you this reference about boson-Fermi models, because we are working with this general boson-Fermi gas. Plus boson-Fermi interaction vertices that we have the more important results here. So this is a generalization of Gaussian condensation and starts from an ideal boson-Fermi channeling gas with electrons as fermions and 2 holes and 2 electrons as bosons. This is the Hamiltonian. Here is the unbound electrons, and this is the operators for 2 electron coupler pairs, and this for 2 hole coupler pairs. So if one turn on the interactions, one have the vertices interactions to form 2 electron coupler pairs or 2 hole coupler pairs. So this is the energy interactions. With this energy interaction to form the Cooper pairs. So to follow diagonalize the Hamiltonian, we must follow the vocabulary side, and we ignore interaction between unbound fermions and bosons with big K, different from zero, and this is the reduced Hamiltonian. The more important here is that the number density, this quantity, is related to electron holes, and the number density for two holes. These two quantities will be the key in the description of the energy gap and some other properties, as well the superfluid density. So this is the thermodynamic potential. From here, one can obtain thermodynamic properties. So the more important aspect here is that this is the excitation energies, but the energy gap here, as defined in this boson-Farmer model, is the square root of the number density of two electrons plus the square root of two holes of Cooper pairs. So this is a key in this boson-Farmer model. So imposing thermodynamic equilibrium conditions one obtains two gap-like equations, one for two electron Cooper pairs and the other one for two hole Cooper pairs, and the number equation follows from the well-known equation of statistical mechanics. So this one have this extended, so we call that in that way extended BCS Boson crossover, because we are working explicitly with two whole Cooper pairs. So this is specifically the three equations: one for two electron Cooper pairs, gap-like equation; another one for two whole Cooper pairs, and the number equation. So let me present to you this very interesting picture that presents for one hand the BCS regime, namely with coupling, and the other hand the strong coupling, namely the BEC theory. So you can see that we are presenting some dimensionless parameter, some dimensionless coupling parameter, and we are using this dimensionless number density as coupling parameter. This is the total number density, and this is the number density of the unbound electrons. So if one change this dimensional ratio, number density ratio, one can stay from in the BCS regime and to move on the other side to the BEC theory. And this is key for change in between coupling regimes. So this is the way to go to the superfluid density. The energy gap is defined as previously mentioned to you, that is the square root of the number density of two electron Cooper pairs plus the square root of two hole Cooper pairs. This leads specifically to two cases. One case for the 50-50 proportions. I mean, is the same proportions for two whole Cooper pairs or two electron Cooper pairs. This is a very special case. One have another special case, 100%, 0% case. This means that one takes only two electron Cooper pairs. And the same happened in the opposite case, 0% and 100%. This means that one takes only two whole Cooper pairs. So if one take these cases about the number density of particles and the superfluid density of this extended crossover can be defined as this way. The dimensional number density is defined by the condensed electron pairs or whole pairs. So one have three cases of superfluid density. The first one for two electron Cooper pairs only, the second one for 2 whole Cooper pairs, and the third one it will be the first case over here is for 50-50 proportions. So if one plots this figure, the energy gap, one can obtain these curves. The black curve is the 50-50 case and coincides precisely with BCS theory. So 50-50 proportions is related with BCS and reflects the weak coupling regime. While one takes the 100 case, namely the 2 electron Cooper pairs, in the weak coupling on the strong coupling regime, changing that dimension of density that I have mentioned to you, the energy gap reduces with respect to the 50-50 proportions. And for comparison purposes, I plot the condensate fraction. But what happened now with the superfluid density defined in this way? This is the superfluid density. So we plot again the 50-50 proportion, the black curve, and we take the 2 electron Cooper pairs case in the weak coupling and the strong coupling. And is compared with BCS and the Gorter-Casimir fluid model, and the superfluid density is below of this case. And this will be a key because we will use this plot to compare with some Cooper superconductors. So this is our first theoretical result on the superfluid density of 2 electron Cooper pairs only in 2-dimensional and 3-dimensional case. So in 3-dimensional case, we are using quadratic energy dispersion relation, while in 2 dimensions, we use linear dispersion relation. So you can see that in 2D, the critical temperature is low from with respect to the 3-dimensional system. But this is a very interesting result because some time ago I met with Professor Ivan Bosovich and I showed you this result and let me compare with one picture that published by him and his group. So we need, obviously, we need to compare with this Cooper superconductor, we need the structural parameters to compare theoretically with these results. But the behavior, the general behavior, that superfluid density is linear with critical temperature, for us, occurs in the strong coupling. So this table is very interesting because we are compared with raw data about the superfluid density. This is the experimental data for some conventional superconductors, and this is our theoretical results of superfluid density in 3-dimensional system and 2-dimensional system for 50-50 case and 100 case. So the interesting aspect of this table is that, once again, this superfluid density in 3-dimensional system is taking the quadratic dispersion relation, and here the superfluid density in 2-dimensional system is linear energy dispersion relation. So you can see that in the 50-50 case match with the experimental data. But the 100 case is below from from the 50-50 case. But in the superfluid density in 2-dimensional systems, it seems that the 50-50 case much better than that 3D system. This picture of 2D system is more realistic, but using the energy dispersion relation, linear dispersion relation. And the last column is the penetration depth. We follow this approximation used by Remura, and you can see that this is the normal penetration depth for 50-50 case, and you can see that 50-50 case is near from the experimental data, but the 100 case is more near than the experimental data, especially for thin and ionium. This is very interesting for us because this can suggest that the charge carriers here are electron pairs. So this is the two-dimensional system, and we are comparing for some coupled superconductors using a 50-50 case and 100 case for the weak and strong coupling. And once again, this 2D system is using a linear dispersion relation. And this is the three-dimensional system. It's the same coupled superconductors, and you can see that in the 3D system, the VCS superfield density is far from the experimental data. And this is expected. It doesn't, because VCS cannot explain coupled superconductors. But this Boson-Fermi model maybe can be explained this behavior, because one can take the two electron coupled pairs in the weak and strong coupling, and since that all experimental data falls between two behaviors. So let me conclude this work. The GBC, this generalization of Gaussian synchronization, is a statistical theory. It is not only a recoupling theory, but addresses strong and intermediate coupling. The superfield density increases as critical temperature. This relation is linear in the strong coupling regime. Solving 50-50 case agrees with that of the superfield density in three-dimensional and the London penetration depth in the weak coupling regime for these conventional superconductors. And we suggest that 100 case match with thin anion, suggesting that two electron coupled pairs possibly be the charge carriers. Solving the 100 case between weak and strong coupling, the superfield density, the reduced superfield density agrees well with some coupled data. So if one ignores the two whole coupled pairs, these results fall below even for the 50-50 case. This suggests that two HCPs are essential in describing superconductivity. So this is our future work. Of course, we continue the study of high temperature superconductors in 2D and 3D with or without two HCPs, and the critical field. Once again, with 2H or without two HCPs. Thank you.